Okay, so in this video, we're going to take a look at the rate of chemical reactions and introduce ourselves to this idea of the collision theory. And so to start off with, let's actually work out what we mean by the term rate of reaction. And the rate of reaction tells us the speed at which a reaction proceeds. So let's write that in. So the rate of reaction is the speed at which our reaction proceeds. Okay, so for example, we have our reaction with these reactants here, A plus B, and they're making products C plus D. And well, the rate of reaction is the speed at which this reaction proceeds. So in other words, how quickly our reactants A or B are making products C and D. So in other words, it's how quickly, or the speed, our reactants, in this case A and B, are forming products C and D. So the rate of reaction is the speed at which a reaction proceeds, or in other words, how quickly our reactants can form the products. And how can we actually measure this? Well, directly we can turn around and say, well, if it's the speed at which our reactants are forming products, let's work out how quickly these products are forming. So initially in our system, let's say that we have this reaction in here. Okay, and we've got all of our A's and B's floating around. Initially, we've only got A's and B's in here. And over time, they're going to react and they're going to form more C's and D's. Okay, so if we work out how quickly our C's and D's are being produced, we have a rate of reaction. So directly, how quickly C and D are being produced. And in the same way, well, for C and D to be produced, A and B have to be used up. So we can also measure it by how quickly A and B are being used up. Okay, so let's take this idea now, and we've got these how quickly C and D are being produced, or how quickly A and B are being used up. But let's work out some ways that we can actually see this happening in a real system. So for example, we've identified that changes in our reactants or products will tell us the reaction rate. But can we do this, for example, by changes in pH, let's say? So for example, if in this case C was a hydronium ion, okay, as the products are being formed, so as our reaction proceeds, our pH is going to decrease because we're increasing the concentration of this hydronium ion. So we would see a decrease in pH. So therefore, a change in pH over time would indicate a reaction rate. So let's find some other chemical properties that can do the exact same thing. So for example, changes in concentration. So similar to this bit here, we're just measuring the changes in concentration of C and D, or decreases in concentration of A and B. What about the change in pressure? So for example, A, B, and D are all aqueous species or solid species, but then our product C is a gas. And well, in this case, as we make more products, the pressure of the system is going to increase because we're increasing the amount of gaseous products. So that's another way that we can measure the rate of reaction. Other examples, change in temperature. Okay, so it might be an exothermic or an endothermic reaction, so it's releasing or it's absorbing heat. We can have changes in color. So, for example, if A is, say, brown, and C is pink, then we're going to, and the other two species are colorless, we're going to be seeing a change from brown to pink over that time frame. So that can indicate to us the reaction rate. We could have the formation of precipitates, changes in voltage or current as we produce electrons. All of those sorts of things, any properties to do with a chemical system can indicate to us reaction rate. So, but what actually causes a reaction to occur? So we need to understand this idea now of the collision theory. So for a reaction to occur, we need collisions. And not just collisions, they have to be successful collisions. So let's see what we mean by that. So we've got let's say that we've got our reaction vessel here. It's happening in a beaker. And we have our reactants here in R, all floating around in this beaker. And what's happening is these molecules, these reacting molecules, they're not stationary. They're constantly moving, okay? So if you imagine a gaseous system here, we've got all of these oxygen and nitrogen and hydrogen gas molecules whizzing around at high speeds. So as they move around, they're moving around at these high speeds, and they're going to crash into each other. And when they crash into each other, we get a collision. But in order for a reaction to take place and a product to be formed, these collisions have to be successful. And in order for them to be successful, there's two things that have to happen. We have to have the correct orientation between our reactant molecules. So let's say that we have a reaction taking place, and it's between hydrochloric acid and sodium hydroxide. And this is an acid-base reaction. So this is going to form a salt, in this case sodium chloride, and water, H2O. So let's find out that these have to have the correct orientation. Let's see what we mean by that. Let's take a hydrochloric acid molecule, and I'm going to write this as chlorine, and that's going to be a nice big molecule, and it's only going to be, hydrogen's only going to be little. So it's going to look something like that as our hydrochloric acid molecule. And let's take our sodium hydroxide molecule. Okay, so that might look something like, we've got our sodium, and then we've got our oxygen here, and our hydrogen's attached to that. It might look something like that, let's say. Okay, but what happens is these are going to come flying in together, okay, and they're going to have a collision, say, about here somewhere. Now, if these molecules are not orientated correctly, a successful collision won't occur. So let's say, for example, this is an unsuccessful collision is favored in this case. Okay, so at this particular orientation, we're not going to have very many successful collisions. But let's change the orientation of these molecules. Let's put the hydrogen up here with our chlorine, or that's a funny shaped circle, and our sodium here. So it's something like this, for example. And they're going to come flying in the same way. But this time, let's say it's the sodium and the chlorine molecules, or the sodium and the chlorine ions are going to react with each other and hit each other, collide in this case. So in this particular case, for example, we're going to have successful collisions is favorable. Okay, so depending on the orientation of our reactant molecules when they collide will depend on whether a reaction or whether a collision is going to be successful or not and actually form a product. So that's one part. Remember, there's two parts. So that's correct orientation's one part. But the other part is that our reacting molecules, so reacting molecules must have sufficient kinetic energy, and I write that as EK, so kinetic energy to overcome the activation energy for that reaction. So remember that each reaction has an activation energy, and in order for that reaction to proceed, we have to overcome that activation energy. So let's take a look at this in more detail. So let's say that we've got this graph here like this. Okay, and this is what we call a Maxwell-Boltzmann distribution. So Maxwell-Boltzmann distribution curve. Okay, and what this tells us is it has the number of reacting particles on the y-axis. And on the bottom here, it has the particles' kinetic energy. And our graph looks something like this. Now, don't freak out at first. We will go through it in a little bit more detail. So what we have is we have, for example, at kinetic energy 0, so these particles, these reactant particles are not moving, we have no reactant particles with 0 kinetic energy. Okay, that makes sense because a lot of our particles, they're always moving around. Okay, they have some kind of energy, kinetic energy associated with them. But let's take this kinetic energy here. Okay, so this might be 0 kinetic energy, and this might be 100. It's just a scale. And here, at about, let's call that 20, we have lots, in fact, we have the most reactant particles here with that kinetic energy. But what happens is that our activation energy actually sits about here somewhere. So this is our activation energy. And remember that in order for a successful successful collision to occur, our reactant molecules have to have sufficient kinetic energy to overcome this activation energy. So only these particles, these reactant particles here, are going to have enough kinetic energy to overcome this activation energy. All of these particles here don't have kinetic energy big enough to overcome the activation energy. So this is even more like, if you think about it, there's not that many particles that are going to have enough kinetic energy to cause a successful collision. There's a lot more here in pink than there are in blue. So this is even more evidence that not all the time we have a successful collision. Only some of the time we have a successful collision. So just to sum up, we've done the rate of reaction, and we know that that's the speed at which a reaction proceeds. Okay, in other words, how quickly our reactants are forming products. And we can measure this by changes in properties of the chemical system. So changes in pH, concentration, pressure, temperature, color, and there's many others. Reaction to occur, we have to have successful collisions, and they have to be successful, not just collide. And in order for that to happen, correct orientation and reacting molecules have to have sufficient energy, kinetic energy, to overcome the activation energy. So if we think about it here, we've got collisions, so successful collisions cause the reaction to occur. Therefore, reaction rate is equal to the number of successful collisions per unit of time. So rate means something with respect to something, and in this case we have the successful collisions per unit time.